three locations, all three locations at the same time. If yes, okay, if yes, then I haven't specified anything about the distance between these 2 points. Okay, if yes, then they can be separated by arbitrary distances, right? Arbitrary distances. So how do we understand that? That means the particle is there everywhere in the universe at the same time. Is it possible? Or what? So what do we now? This particular way of stating, okay, that so when can a particle be at all these three states, at all these three locations, or at many locations? Okay, so we ask this question: when can a particle be at multiple locations? As described by a valid superposed state. Okay. Now a particle, as you may imagine from your classical understanding, that it is a, in classical mechanics we have this concept of point masses. Point masses means even though mass has certain volume, we say that it is a point mass. That means the position is a point in the space. Okay, so if it is like that, then we will not be able to understand this. So what is the way out? One way to understand is that the if it is a wave, okay, if it is a wave, then we can say that, okay, this is how the particle is. Now this wave is there at many locations, right? If it is a wave, then it can be understood. Okay, I am not presenting it in the way historically these ideas came. I am trying to present it in a way that it is easy to understand. Now, what is the origin of wave nature, or what is the origin of some dual nature that we are talking about? You can completely get rid of this dual nature if you just want to learn quantum mechanics without bothering about this dual nature. It is possible. All that what you have to do is you have to understand that superposition is a necessary structure. Once you understand superposition, and once you say you have superposed state, that means if you want to physically understand how a superposed state is there according to the argument that I have given, you have to think of that as a wave. Then of course you can ask what kind of wave it is and all that. Okay, so the wave nature actually, even though historically first people proposed a wave nature and then came Schrodinger equation and then superposition, but now from our what we are trying to put an effort is that first we are trying to understand that superposition is a requirement from our beam splitter experiment and so on. because we observe interference, superposition is necessary. Now you want to interpret the superposition, then you have to bring in a wave nature. Is this logic? I'm attempting a new logic. This is not probably what textbooks tell you, but if I thought that this is an easy way to understand. Okay, any questions or?
But sir, like
Sir,
go ahead.
that last point, can you repeat when you say superposed? That I missed, sir. Means
No, essentially what I'm trying to say here is that
yes, sir.
if you say that so I'm making 2 points. One is if you have interference that is observed, right?
Yes,
Nature
sir.
exhibits interference.
Yes,
Now, if you want to understand interference, superposition of states is the only way.
yes, sir.
Okay. If this beam splitter is not creating this superposition, then the interference cannot be understood in the Mach-Zehnder. We have seen in the
Yes,
last class, right? So if the beam
Yes, sir.
splitter is not creating this interference,
Yes,
then
sir.
interference cannot be explained.
And yes, sir.
So interference, observation of interference is a necessity to understand that the basic superposition structure is necessary. Is that point clear?
Yes, sir. Yes,
Or
sir.
is this convincing?
Yes, sir. This I got.
Now I am trying to argue this. This is not very new. I mean, this is not new, but what I am trying to argue now is probably not well presented. So what I am trying to say is that now superposition is valid.
Yes,
So
sir.
I am saying now you have, let's say, 3 positions, x1, x2, x3. Then I write a position state in this fashion.
Yes,
This is
sir.
a valid state. Correct? This
Yes,
is a
sir.
legal state.
Yes,
Now
sir.
I am asking, what does that mean? Does that mean that particle exists at all 3 locations at the same time? Okay.
Yes.
Now, if your answer is yes, okay, if you wanted to interpret that way, then you ask a question, how can a particle be at all the 3 locations? Only if it is a wave.
Then only, yes, sir.
Then only it is possible, right?
Then only
So
it
that
will
I
stay.
have to interpret this wave nature as an interpretational necessity for explaining the superposition, or for saying superposition in words. What is fundamental is the superposition structure, and you want to say something about superposition or what superposition means,
Yes, sir.
then you have to say that it is like a wave.
Yes, sir. Sir, here one doubt, sir.
Ah.
Sir, when you say it is spread, this superposition, does it represent in actual coordinate space or somewhere, or it is? Can we think it in physically, or this is just a superposition in some abstract space?
No, superposition. See, it is, even if it is an abstract space.
Yes,
Okay. So, like what we discussed in the last class, maybe it is worthwhile to recall that.
Yes, sir.
So I said that we have some kind of a vector, right? Quantum state is kind of a vector,
Yes, sir.
right?
Yes, sir.
So it's a vector. Okay, we may represent this as a ket.
Yes, sir.
Okay, such that this is normalized. Correct?
Yes.
So in
Yes.
fact, I call this as a unit vector.
Yes,
Okay.
sir. Yes, sir.
Now any other vector will be a multiple of this.
Yes, sir.
Okay. If you take a real vector, let's say you take a I cap, which is a unit vector.
Yes,
And then if you say that I want set of all vectors with unit magnitude, that is the only vector I cap.
yes, sir.
Any other vector along x-axis is going to be of a different norm.
Yes, sir.
Correct?
Yes, sir.
So we have only one unit vector.
Yes, sir.
But if you are allowing complex vectors,
Yes, sir.
then I can have infinitely many vectors of this type, e to the I theta into psi.
Yes, sir.
Correct?
Yes, sir.
So this is a space set of all vectors of this type, theta belonging to 0 to 2 pi.
Ah,
Okay, this entire set of vectors will have unit norm.
yes, sir.
Correct?
Yes, sir.
So this is essentially different vectors. Correct?
Yes, sir.
These are different vectors, and they all have the unit norm.
Yes, sir.
Okay?
So dimensions are
Huh?
like when you say this only a psi, 1D, the dimension of that is vector space is 1, right? I cap only. Now
No,
by
if there is only one vector.
yes, sir. Yes, sir.
Here you have many unit vectors themselves, right?
That you.
So usually in quantum mechanics, this has got a name. This is called a ray.
Okay. Yes, sir.
Ray, because this is this entire. Uh, so this is infinitely many vectors. Correct?
Yes, sir. Yes, sir.
So this is a ray. But so mathematically, the structure is like this. Okay, mathematically, the structure is like this. Now, what happens? But of course, there is. Okay, so let me just say that now when you come to superposition, okay, so you may have one vector psi and another vector phi. Okay, so this is a vector and this is a vector. Now there can be another vector which is alpha times psi plus beta times phi. Correct? Now this is essentially uh, for several values. I mean for any alpha and beta, this is a valid state. Correct?
Yes, sir. Yes, sir.
Alpha, this is just a so if you understand this, let's say that I have so let us look at just a two-level system.
Sir.
Okay, let's say I have two-level system. Okay, just to make things clear, let's say I have two-level system. That means I have a level 0 and a level 1. Okay. Now we ask a question: what are the valid states of this system? Valid quantum states. What are the valid quantum states? Is it just 0 and 1?
No, sir.
So what are the valid quantum states? If I ask what is the state, okay, so the state is basically, so valid quantum states, actually this form a vector space. Valid quantum states form a vector space. That means I can now define, let me call this as H is equal to, basically it is a span of this 0, 1. What does that mean? That means it is set of states alpha 0 plus beta 1 such that alpha and beta are numbers and modulus of alpha square plus modulus of beta square is 1. This is the state space, correct? This is the state space. Now I'm just, let's say that I have only one single state system or a single level system. Okay, so let us say there is only one state. One state. And let me call that one state as 0. Now, what is the state space? State space for this is, so let us call this as H2 and let me call this as H1, is equal to alpha times 0 such that alpha is a complex number and mod alpha square is equal to 1. That's what I have written here. I'm just writing same thing here. Now, what is this one? If alpha is a complex number and mod alpha square is equal to 1, that implies what? This alpha can be written as some e to the power I theta 0 such that theta is between 0 to 2 pi. These two are same sets, right? I can recast this set in terms of this set, right? So this is the state space corresponding to a single state, and that is what I am calling it as a ray. If you have two states, then this is the state space. If you have 3 states, then you can write down accordingly this, correct? So now imagine physical situation. Let's go back to our 2-level system. Okay, so we have 2 levels. Let's say this is ground state and this is excited state, 0 and 1. Okay. Now you ask a question, 0 and 1, and something like 1 by root 2 times 0 plus 1. Okay, is a valid state, correct? Is a valid state, correct? Now, if this is the state, okay, in this state, let's say this is an energy state. So this has got an energy E0 and this has got an energy E1. So in this state, okay, what is the energy of the particle?
So we can talk about the expectation value of energy, sir, of the particle, but not exactly the energy.
Correct. So what I'm saying is that if you ask this question is like, okay, so this question is like so similar to the question that if the state is let's say C1 times x1 plus C2 times x2 plus C3 times x3, what is the position of the particle? Okay. Now, in both the cases, what is happening is that in both the cases, the answer is that in this case, So when I say what is the energy of the particle, if I know answer, when do I say I know the answer? When I can predict the outcome of a measurement. I say that energy is this much and I make a measurement, I find the energy to be that much. Then I can answer this question with certainty. Same thing, I will say that this, if the position of the particle is x3, I make a measurement and find it as x3, then I can say that I know the position of the particle in this state. But in these two cases, the answer is we don't know. Okay, or in this particular case, we can say that no definite energy. In this case, no definite position. No definite energy, no definite position. So what do? We will have to resort to the experience. Okay. So let us say that, let us stick to, once you understand the similarity of these two questions, then let us stick to this one. Let's say that I have, let the two-level system be in a state. Let me take a particular state. So I will call it as some psi is equal to, let's say 1 over root 3 of 0 plus square root of 2 by 3 of 1. I have made sure that mod square of this and mod square of that is equal to 1. So I'm just giving some numerical values for these coefficients. Okay. Now, let's say that we have an energy meter. Okay, so we have an energy meter. That means it can measure energy. Energy meter. And we do not have a definite energy for the particle. We do not have a definite energy for the particle. That is what we, if it is 0, we can say the energy is E0. If it is 1, we can say energy is E1. But if it is in this state, we do not have a definite energy for the particle. Now we ask a question. What will be the result? What will be the result of the measurement of energy when the particle is in the state psi? So you are going to take your energy meter and you measure the energy of this particle. What will be the result? So if you do this experiment, then we can make some meaning out of not having a definite energy. So see, when you say you are using a mean, give some number, right? Okay. So for example, the number, what kind of number it gives you? Let us say it may give you some, so E0, E1 are the energies of these two. Maybe it will give you some intermediate energy. Okay, so that is the question that we are asking. What will happen to a measurement?
Sir, I think we won't get any intermediate energy. Like we'll get like if we measure it n times, then n by 3 times we'll get E0, and 2n by 3 times we'll get E1.
So for a given measurement, okay, so for a given measurement, what do we get? If we ask this question and the answer is I don't know, why I don't know? Because we cannot predict.
Sir, but still we can predict the probability of getting a state, no, sir?
Yeah, I'm coming to that. So for a given measurement, we don't know what we will get. But now, so this is somewhat like we have come across this situation, right? For example, if you toss a coin, and ask what is the outcome for a given task. If you ask this question, what is the answer? I don't know. That is the answer. Correct? In the same way, let's say that you have a photon like this and you have a polarizer like this. Okay. Now, if you ask what happens to a given photon, at polarizer, answer we don't know. That is the same answer. Correct? In the same way, let's say you have a photon and then you have a beam splitter. Okay. Now you ask a question, a given photon will be transmitted or reflected I don't know. Now you understand all of them are on same footing. Okay. Essentially, we don't know what is the outcome of a given measurement. So if you go back to, so when we did this polarization thing, no, we took we used a large number of photons, right? So
Sir.
now you are going to say that I have a source. Okay, this is a source which is giving rise to particles. Okay, so let's say I am getting particles like this. Now each of this particle is in this state psi, which is equal to root 1 by 3 0 plus root 2 by 3 1. Okay, each of this is in this state. Now I have here an energy meter. Now we are going to record the measurements. Now what happens is if you send in large number of particles and looked at your energy results, you are going to get n by 3 times E0 times E1. This is exactly like what we saw in this case. If you have a detector here, D1, and detector here, D2, you will have n by 2 times, n by 2 photons come here and n by 2 photons come here, right? In the same way, we get n by 3 times E0 and 2n by 3 times E1. Now, this is what is related to these coefficients. So now we can say in general, if your psi is equal alpha times 0 plus beta times 1, such that mod alpha square plus mod beta square is equal to 1, then of getting E0 as the energy is mod alpha square. Probability of E1 is equal to mod beta. Okay, so by looking at a quantum state, okay, so I go back to this question. If a quantum state is given, okay, if a quantum state is given, we don't know what is going to be. Okay, so let's say if a quantum state is given, then given such as psi is equal to 1 by root 3 0 plus root 2 by 3 1. We do not know a priori the outcome of the measurement outcome of the energy measurement. We do not know a priori. Beforehand, we don't know what is going to be the outcome. Okay. Now, in a given measurement, or let me say already, the outcome is randomly one of the two, namely E0, E1. Okay, it is going to be one of. So what information that quantum state contains? So if the quantum state, contains information of the possible outcomes. Just like in coin toss case, we know possible outcomes are head and tail. So quantum state contains information of possible outcomes. So since I have 0 and 1 here, 0 and 1 here, it will be E0 and E1 only. In the same way, I have x1, x2, x3. When you make a position measurement, you will get one of those three. So quantum state contains information about the possible outcomes. Further, it also contains the information of the respective probabilities of possible outcomes. In which way? The probability is nothing but the coefficients modulus square. If alpha and beta are there, probability of E naught is mod alpha square, probability of E1 is mod beta square. Okay, so this is what now suppose, so now we'll just develop this language carefully. Let's say that if the state is, let's say, 0, this is also a valid state, right? Then what is the energy of this? What is the energy of the particle? Energy of the
Is
particle.
E0?
Yes. So energy of the particle is E0. It has a definite energy, right? In this state, it has a definite energy. Okay. So if you measure energy, you will get E0. So let's say you have a beam of particles. Every particle is in 0 state. Every measurement will give you E0. So probability of E0 is 1 and probability of E1 is 0. Correct? That means it is just like a polarizer. If the polarization direction and polarizer's axis direction are same, every particle will come out. Right? In that way, so if we have this kind of a state, so we will write it like this. So we say that energy is sharp in the state 0, because there is a definite energy. Okay, we say sharp in this state. Now, what about energy in the superposition state? In superposition state, when you make energy, when you do energy, what happens? It is E0, E1, E0, E1, like this, randomly it is coming. Okay. So then we say that energy is dispersed in the state like 1 by root 3 0 plus root 2 by 3 0. Because
So
the
1.
measurement results are
Sir?
spread.
So root 2 by 3 1. Sir?
Yes. Yeah. Yeah. So energy is dispersed. So two, words I am introducing. One is sharp, and this is dispersed. Okay, so energy is dispersed in this. In the same way, you can talk about position is dispersed in that state. If the state is just one of the position, then position is sharp. So any property, okay, so that can be dispersed or it can be sharp. It is sharp in certain states and it is dispersed in certain states. Okay. Now, okay, so if you understand this, so there is one. So now what happens? So if energy is dispersed, okay, so in the state, one over root 3 times 0 plus root 2 by 3 times 1, energy is dispersed. Okay, and results of measurement vary randomly among E0 and E1. Okay, then we can ask a question that what kind of statement can we make about the energy of the particle? So ask a question, what can we say about the energy of the particle in this state? Okay, this is an important question because I want to have, see, I cannot say that the particle doesn't have energy if it is in this state. It doesn't have a definite energy, but then I must be able to say something about energy of the particle, isn't it?
Yes, sir. The energy is not well defined, I think.
Yeah. So okay, it doesn't have a definite energy in the sense that measurements will not give you any particular value, but from the values that we get from the define some energy, so that a particle in any state we should be able to define some energy, right? So if you want to do that, now go back to the case where the energy is sharp in the state 0. Now let's say that you have n number of particles and every particle has got same state 0, then you will get E0 all the time, right? So now what happens, you would like to define this, you would like to define this energy for the particle, which when energy is sharp in that particular state, okay, then it also has a definite energy, and the energy that we define also coincides with that definite energy. But when there is no sharpness, that is, energy is dispersed, it doesn't have a definite energy. But what we do generally when there is a dispersion is that we will use statistical quantity like average value of energy, and then we can also talk about the extent of dispersion by looking at the variance of the energy, correct? So these statistical quantities we can use. So what can we say about the energy of the particle? So we define energy of a particle in any state to be its average value. Average or mean value, which is called an expectation value. Expectation value. Now note that whether energy is sharp or not, you can define expectation value. Okay. If it is sharp, then the expectation value will become the definite value. If it is not sharp, then expectation value is the only value that you can define. So in general, we say that the energy of the particle is the expectation value. Okay. So why we have to define this? Because it's not that only for some states. Let's say that I have a space of infinitely many states. Okay. So for example, in two-state system, I have a state which is given by alpha 0 plus beta 1, such that alpha, beta are complex and mod alpha square plus beta square is equal to 1. How many states are there? There are infinitely many states. This is a two-dimensional vector space. Correct? It's a two-dimensional vector space. Now, I have definite energy, or in other words, energy is sharp in states 0 and 1. Only two states. Out of infinitely many states, energy is sharp only in two states. Okay, that does not mean that the particle is going to be in this state or in this state always, right? The particle most likely will not be in these two states because there are only two states out of infinitely many states. So what will be the energy of the particle if it is in some states? All other states are energy is dispersed in all other states. Okay, so sharp kind of only in states 0 and 1, and in all other states, and it is dispersed. Dispersed in all other states. Okay, so if we define expectation value, so for example, a state like this, okay, so we have already discussed this. So alpha 0 plus beta 1 mod alpha square plus beta square is equal to 1. So this state contains what? If the state is like this, then it gives you information that two possibilities are there, E0 and E1, and probability of E0 is equal to mod alpha square, and probability of E1 is equal to mod beta square. Okay, now the expectation value or the average value of energy, you can write it as mod alpha square into E0 plus mod beta square into E1. Okay, now what happens? So this is something which you can define. Okay, this can be defined. This can be defined for all alpha comma beta in complex numbers. okay, such that mod alpha square plus mod beta square is 1. This can be defined. So this is, you can define whether the energy is sharp. Now what happens? For example, for this state, we have alpha is equal to 1 and beta is equal to 0. That implies what? That implies average energy is simply E naught. There is a definite energy, and average energy becomes that definite energy. Similarly, for 1, alpha is equal to 0 and beta is equal to 1. That implies average energy is equal to E1. For any other alpha beta, this is the average energy. So please understand that if I define the expectation value of the as the energy of the particle in that state, I will be able to assign energies to all the particles, to all the states. Wherever the energy is sharp, it will become that sharp value of energy. If energy is dispersed, you have some measure of energy, so that every state has some energy. Now I have chosen energy as a property. You can choose any property. You can choose momentum, you can choose position, you can choose angular momentum, you can choose any property of the system. This is how it looks. So the expectation value is the value that can be assigned as the value of that property for all states of a quantum system. Okay, so I would like to just break here and see if
Sir,
you
I
have
have one
absorbed
question.
it or any question. Yes.
Sir, here expectation value need not be the values E1 and E2. That means we know particle will be either in E1 state or E0 state, but the expectation value is like not E1 or E2, not E1. Like how to understand this?
What did you ask again? Can you ask if the particle, you know that particle is either in this state or in that state?
But expectation value is not both, but it's like an intermediate or in between them. But particle can't be in that value.
Correct.
So how to understand that?
Yeah. So what I'm trying to say here is that the expectation. See, we have to. So we are asking a question. When the state is alpha times 0 plus beta times 1. Okay. Is that question clear? What is the energy of the particle if the state of the system is alpha times 0 plus beta times 1?
Yes.
Okay. So how do we obtain an answer for this? By making a measurement. So when we measurement, what result we are going to get is that you don't know beforehand what is going to be the result, but the result is going to be either E naught or E1. Okay. We cannot predict which one is going to be the result, but result is going to be one of these two randomly. You don't know beforehand what is. It is just like tossing a coin. Now to get more information about this, let us use large number of particles prepared in the same state, alpha 0 plus beta 1. Then we discover that the answer is going to be E0 or E1 randomly for every particle. But if you look at the results of the large number of particles, some mod alpha square fraction, if you say n number of particles, mod alpha square into n times, you will get E0. Mod beta square into n times, you will get E1. Okay, so this is our experimental result. Okay, you follow that?
Yes,
This
sir.
is our experimental result. Now from this, what we can say? So this is what I have been trying even with the polarizer experiment, right? So we look at the experimental result, and from that result, we can ask what is it that we can say. Okay, so now the question is, is our experiment result. There's no single energy that I am getting. I am getting the value of energy as E0 and E1. And from the quantum state, I can say that mod alpha square is the probability of getting E0, because mod alpha square n times is what E0 is coming, and mod beta square is the probability of getting E1. So the coefficients, once I know in the quantum state, then mod square of that will be my probabilities of getting E0 and E1 respectively. Now with this kind of information, I am now going to assign, okay, I'm going to postulate or assign or assume whatever axiomatize. I'm going to say, I'm going to define the energy of the particle in a energy of the particle in a state where energy is dispersed as the average value of the measurement results. Okay. I'm going to assign this. Why am I going to assign this? Because there is a requirement that energy exists for all the states. Whatever is the particle, in whichever state it is, there should be some energy for the particle, and I should be able to assign some value for the energy. Now in this theory, I'm going to assign energy for a particle in that particular state is the average value of energy, average value of all the measurement results. Okay, and that is what we are calling as an expectation value. Now what happens if the state is such that energy is sharp in this state, it has definite value of energy. Now the way I defined expectation value is that expectation value is same as the definite value of energy. In other words, since their average value is going to be the same value, I can generalize it and say that one way of assigning energy for each state is to define the average value of this measurement results. This is an assignment, remember.
Okay.
This is an assignment. I'm going to assign this is the energy of this system particle in this state.
So expectation value doesn't mean that when you do an experiment, you will expect
You will not get that value.
average. Okay.
Yes, you will not get that value.
Okay, sir. Thank you.
But sir, if we like use an equipment that is not very sensitive, like that takes a lot of photons, a lot of electrons to give a result, to give an outcome. So in that case, we'll get the expectation value. Average value we'll get. Like
yeah.
So that's
average. You will not get. See, the point is two things here. One is you are going to. Okay, you are talking about. So, are you talking about some weak measurement kind of thing?
I'm talking about an equipment that is not very sensitive, that it can detect one photon. Like it has some cutoff intensity that above which threshold intensity it will detect. It will throw a value. So we need a lot of photons for the equipment to work. So in that case, we will get the expectation value in the meter.
Well, I think that is also kind of a that that is not in the spirit of the way that we are talking measurement. Okay, so when we say measurement, let's assume that the apparatus is kind of a classical apparatus which will give you one of the two results, either E0 or E1. Okay.
Okay, sir.
Let's not worry about kind of variations in the experiment. Is always like that. The measurement will give you one of things. Now, yeah. So this is okay. I think the screen sharing has stopped. Let's see. My screen is not shared, right?
Sir,
no, sir.
It is not visible.
Oh, I think that the thing itself has gone. Just give me a minute. Okay, so what I'm asking is that so the kind of motivation for defining this expectation value. Okay, so now you see the expectation value. So the the requirement of defining an expectation value is also because there is superposition, isn't it? If there is no superposition, there is no question of dispersion. If there is no superposition, there is no question of dispersion. So there is no need to define any expectation value. Correct? So if there is no superposition, there is no uncertainty. There is no indefiniteness. There is no dispersion. So there is no randomness. There is no requirement of defining probabilities. Correct? So superposition of states are the description of quantum state in terms of superposition is what is responsible for all the postulates that we have. What are the postulates we have? We say quantum state is a vector in a Hilbert space or a vector space, and then the probability quantum state defines the probabilities, quantum state defines the possibilities and also probabilities, and then the value of any property in a given quantum state is its expectation value. Okay, so these are kind of three postulates on which quantum mechanics rests. Okay, now okay, so now let us try to. So I have. Let's try to develop this into the language that we are familiar with. Okay, so now let's say that let's say that we have a kind of entire x-axis. Okay, so this is x-axis. Now I have a particle in one dimension, and position of the particle can be any point on x-axis. Okay, then what do we say? The general position state okay, how do you write a general position state? So let us say x is the position x of the x-axis. Okay, so it can be anything. So let's say this is your x. The next one is another position. So every point is x. Now you see that this position is continuous. Okay, now each of this position can be. So what you have to do? You have to say that just like alpha times 0 plus beta times 1, I have to have a complex number here, right? So let me call that complex number, because x is continuous, that for every x there will be a complex number. So that is a complex function of x. So let me call it as psi of x into x. Now if I have a discrete thing, let's say I have 0 and 1, I say alpha 0 plus beta 1. But now x is continuous, and hence I have to, the summation has to be removed, and then I have to do an integration. So this is the most general state. Okay, this is the most general position state. Okay, So I don't know what to call this. Maybe I call this as some phi. So most general position state is like this. Okay. Now what does this psi of x mean? What is the position, or what are the possible positions? Okay, so when position is measured, the possibilities are all points in x-axis. All points in x-axis. Correct? Now, this is a continuous this thing. So when you have a continuous variable, now you ask a question, what is the probability that the position is equal to some x prime, let's say. That is given by modulus of psi of x prime, the square, because this is a coefficient, right? So this is what we call as probability.
Sir,
Yeah.
this has to be zero, no? Means defining probability is meaningless when it is continuously varying, right?
Correct. So what I'm trying to say is that if you say that probability at x equal to x prime in a continuous variable, a point is actually there is no measure for that point.
Yes, sir.
Okay, so imagine that you have an x prime here. You must define some small interval dx. Okay, and define probability like this. So probability at x equal to x prime is 0. So probability, okay, maybe I should write it like this.
Here it can be like probability of finding particle.
So probability
prime and x prime plus dx.
Yeah. So probability of the position of a particle in x prime and, or you can say in this interval x prime and x prime plus dx, that is equal to modulus psi of x prime the square into dx. Okay, so this language has to be slightly different because of continuous variable, and psi of x prime or psi of x for that matter r square is now called probability density. Okay, and this psi of x is what in the earlier days we called as wave function. Even now we call it as a wave function.
Probability amplitude.
It's a probability amplitude. Psi of x is the wave function, and this is the probability amplitude. And this is related to probability density. This is what we call as Born rule. So Max Born had suggested that the solution of a Schrodinger equation is a wave function, and mod square of the wave function is the probability density. Now, if you see this psi of x, the psi of x is nothing but alpha. And in general, if you say that you have all positions are possible, what does that mean? When is it possible? Only when there is a wave nature. When the particle has a wave nature, then all positions are possible. Okay, because possibilities are several positions and each position has certain probability. we interpret that as a wave nature. But essentially, it is a superposition of all position states. Okay, so essentially what I'm trying to say is that if you accept, I mean, if you understand that superposition of states is a necessity in quantum mechanics, and don't ask what does it mean of having a superposition of position states, then you don't have to worry about wave nature. Wave nature is not required to be considered at all. Okay, so that is the point I am trying to make. So the wave particle duality, etc., all this is in some sense a semantic aspect of this whole thing. But if you understand superposition, mathematically the superposition is the crux of the matter, then I think everything in quantum mechanics can be easily understood. And a lot of mystery can be taken out of quantum mechanics.
Sir?
Yeah.
Sir, you said superposition, sir. If we ask, means at a particular instant, where is the particle? Then this wave nature naturally comes from superposition, right?
Correct. No, at a particular, see, the point is, if you look at some of the arguments in quantum mechanics, so one of the issue they try to write is that particle can be there at same location, at different locations at the same time.
Yes,
It can have different speeds at the same time,
yes,
right?
Sir. Yes, sir.
So,
Yes, sir.
so this is the language, you know. This is the language in which this superposition is interpreted. Okay, but what I'm saying is that this is a kind of choice. You don't have to interpret that way, right? Like, for example,
means without affiliating to any one of the choice, either particle aspect or wave aspect,
yes,
one can do
yes,
both.
yeah, one can do. So that is see, why am I introducing it this way?
Yes.
Is because I don't want to create any mystery that this is intriguing aspect of this and things like. There are certain nice aspects of this. Superposition itself is sufficient to understand many things.
Yes, sir.
So that is why I'm concentrating on this superposition. And superposition is also there in waves. That is why the wave nature comes practically, I mean, to the rescue of interpretation.
Yes, sir.
Because we have a superposition of waves, right?
Yes,
so
sir.
that is why when you say that there is a superposition, that means it is like a wave-like behavior.
Yes, sir.
That is how the wave nature comes.
Yes, sir. Thank you, sir.
Any other question? I don't know. I'm hoping that I'm clarifying things, but I hope I'm not confusing. If there is someone who is getting confused, or do you think I should introduce quantum mechanics in the standard way in which textbooks introduce? If you want me to do that, it is easy for me. I can do that also.
Sir, honestly, this way is really nice.
So something different, right? So at least,
yeah.
I hope you all learn quantum mechanics in the routine way in your colleges, but I'm trying to provide slightly offbeat perspective on this.
I am learning for the first time, sir. So it's like a new thing.
But you might learn again. That time it will be different.
This semester I am learning.
Yeah. So that time I think it will be different, and you can probably see the connection.
Yes, sir.
So should we proceed like this?
Yes, sir.
Yes, sir.
Okay.
Yes, sir. This is nice, sir. Means here we don't bother about what is complementative, when it will be particle, when it will be wave.
So I'm trying to little bit clear of that one.
Yes,
of course, I'm not saying that. So I'm trying to. I'm trying not to give too much importance to those things.
Yes, sir. Yes, sir.
Okay, so okay, so then I will stop here, and we will continue in the next class.